Welcome to the first video in a series of videos intended to give one an introduction to topics they would encounter in first semester general chemistry. As with lectures, these videos will not be as detailed as a textbook and should be seen as a supplement to a general chemistry textbook, not a substitute for one. In this video, I'll introduce several definitions important to science and chemistry so that we have a common vocabulary for subsequent videos. I anticipate that this will be the longest video in this series by far, with most other videos being on the order of 5 to 10 minutes long. So with that, let's go into explaining what science and chemistry is. So science is a tool by which one can derive knowledge about the universe in a systematic fashion. So science I see as a tool and not necessarily a subject of study. The physical sciences apply that tool towards understanding the physical and natural world. One typically applies the scientific method when one studies these phenomena. Since Galileo in the 17th century, the scientific method has been our best tool for understanding how the natural world works. The scientific method is simply a systematic manner in which one derives knowledge and understanding. We can make a schematic for the scientific method as such. So typically, one will make some observation or perform some experiment. From those observations, one can make inferences that will lead one to formulate a hypothesis. A hypothesis is simply an evidence-based explanation for how a specific phenomena will behave or what the underlying mechanism that produces that phenomena is. A hypothesis has three characteristics. It is predictive, it is testable, and it is falsifiable. If you can't falsify a hypothesis, or I should say potentially falsify a hypothesis, then it's not a hypothesis and you're not doing science. Because a hypothesis is predictive, you can predict another observation based on another experiment. And that additional observation can support or refute that hypothesis. Once one has a very well supported hypothesis, one can derive a theory. A theory is an overarching system of ideas that's based on a very well supported, verified hypothesis. A theory is predictive and it's explanatory. Furthermore, it's explanatory independent of the specific observation being made. Because a theory is an overarching idea, one can derive hypotheses from theories, one can predict observations from the theory. So a theory can be thought of as a super hypothesis. One often hears about laws, and laws talked about in the same way as a theory. A scientific law is predictive. A scientific law, however, is not explanatory. So, for example, with Newton's law of gravity, one can predict the force exerted on a mass by a different mass in relation to the distance of the masses, their mass, and some constant for gravity. This can be contrasted with Einstein's theory of general relativity, which is predictive, but it also is explanatory. It explains why gravity exists in terms of the curvature of space. So chemistry is a branch of the physical sciences that concerns matter and how matter interacts with other forms of matter or energy or other forms of matter and energy. We can define energy as simply the capacity of some object to do work. In general, energy is divided into potential energy and kinetic energy. Potential energy is the energy that's possessed by an object because of factors such as internal stresses or its position in space. So, for example, a ball that's up on the top of the hill has more potential energy than a ball that would be on the bottom of a hill. Kinetic energy is the energy that an object has simply by virtue of it being in motion. So we can think about this in terms of a balloon. So if you have a filled balloon that has a large internal pressure, that balloon has some potential energy in it. It has a large pressure on the inside, so it has a large degree of internal stress. Once you open that balloon up, all of that potential energy can be converted into kinetic energy. So the air that's in that balloon moves out, converting that potential energy, that internal stress, into kinetic energy. In chemistry, we're going to define potential energy as the energy that's contained within bonds between atoms and between molecules. So the energy that holds atoms together will be defined as our potential energy. We'll be defining atoms and molecules shortly. As an example, trinitrotoluene, TNT, has a lot of potential energy in those bonds. When you ignite TNT, that potential energy gets converted into kinetic energy. Kinetic energy for this class will be the movement of atoms or molecules. So when TNT detonates, the molecule of the trinitrotoluene gets converted into gas molecules that expand rapidly apart from that central molecule. So these gas molecules that I have depicted in this box would be moving all about. So we've defined energy. Now we need to define matter. Matter is any substance that has both mass and volume. The definition that we're going to use for mass, which is the most simple definition, is it's the measurement of the amount of substance that one has. Mass is different than weight. Weight is simply a measurement of the pull a gravitational force has on an object. So, for example, a long time ago, I weighed 180 pounds on the Earth. This converts into about 82 kilograms of mass. If you were to take me from the Earth and place me into a void where there's absolutely no other objects around, my mass would still be 82 kilograms, but I would weigh 0 pounds. In contrast, if you took me and put me on Jupiter, my mass is still 82 kilograms, but my weight changes to 455 pounds. Mass does not change regardless of where you are in the universe. Weight changes depending on the gravitational force the object happens to be in. Volume is the amount of space a 3D object occupies. There's a specific ratio that we talk about, the mass to volume ratio in chemistry. This is density. Density is just the amount of mass divided by the volume that that object occupies. Because all forms of matter have mass and volume, all forms of matter have density. So we've defined matter as anything that has mass and volume. And this encompasses a lot of different objects. Everything from small subatomic particles like protons, neutrons, and neutrinos, to creatures such as walruses, to the universe as a whole. All of these have both mass and volume. For chemistry, we limit ourselves to studying atoms, compounds, and molecules. Atoms, compounds, and molecules all have mass and volume. An atom is defined as the smallest unit of a chemical element. Atoms of the same type make up elements, which are substances that cannot be broken down any further by chemical means. There are currently 92 naturally occurring elements. One could make an argument that there's really only 91 because of technetium element 43, but essentially the first 92 elements on the periodic table are naturally occurring. They can be found in nature. We'll be talking a lot about the periodic table of the elements later on in the course, but it's just a systematic way of organizing different elements according to similar chemical properties. So we have 92 naturally occurring elements, but currently there are 118 known identified elements. Everything past uranium has to be synthesized in a lab, and they have very short lifetimes. In addition to atoms and elements, we also talk about compounds. Compounds are substances made of two or more elements. The smallest unit of a compound is referred to as a molecule. So I'm going to give you examples of these on the next slide. So as an example, we can look at sodium. Sodium is an element. It's a highly reactive metal. If you have sodium, you can't break it down any further by doing some chemical reaction to it. You have to use a high power technique that's non-chemical. The sodium atom is the smallest unit of elemental sodium. Sodium is highly reactive and you can easily form compounds out of it. So for example, you can make the compound monosodium glutamate, which is a food additive. If you break down monosodium glutamate into its smallest unit, you get a molecule of monosodium glutamate, which is made of carbon, hydrogen, oxygen, nitrogen, and sodium. Matter is found in 4 different forms: plasmas, gases, liquids, and solids. Defining a plasma is an ionized, highly conductive gas. So the molecules of neon in a neon lamp have been ionized, or they've been converted into positively charged atoms of neon and negatively charged atoms of neon. Most chemists do not think about plasmas and do not work with plasmas. So for this class, we're going to pretty much ignore plasma as a state of matter and focus on gases, liquids, and solids. A gas is a form of matter that has a defined mass, but no defined volume. The volume of a gas depends on the container it happens to be in. Because it does not have a defined volume, it doesn't have a defined density. It has a density, it's just simply not defined. It varies on the size of your container. The reason for this is because gases will expand to fill the volume of whatever container they happen to be in. So, for example, the gas that's contained in that O2 container, that blue O2 container, will have a density that's related to the size of that container because the gas particles are filling the whole container evenly. The reason for this is that the interactions between the individual gas particles are weak. They don't adhere to each other strongly. So because of that, they can just fly apart and occupy whatever space they happen to occupy, regardless of which other particles of gas happen to be around them to a first approximation. A liquid has both defined mass and defined volume. It's also a freely flowing substance. A liquid, however, has no defined shape, so it'll conform to the shape of whatever container it happens to be in. Notice I said conform. It still has a defined volume, but it has no defined shape, unlike a gas, which expands to fill the container. It has no defined shape, and it also has no defined volume. A solid, on the other hand, has both a defined mass and a defined volume. It therefore has and it also has a defined shape. So the difference between a liquid and a solid has to do with defined shape. If we look at the individual particles in a solid or a liquid, what we find is that those individual particles strongly interact with one another. So they hold on to one another, allowing them to have that defined volume. When we talk about chemical compounds and chemical substances, we typically also talk about mixtures of these compounds and these substances. So a pure substance is matter that does not vary from sample to sample. So when we're talking about elemental sodium, that lump of elemental sodium was a pure substance. When we're talking about those crystals of monosodium glutamate, those individual crystals of monosodium glutamate were pure substances. A mixture results from the combination of two or more pure substances. So, for example, we can think of vinegar. Vinegar is a mixture of water and acetic acid. So, it's a mixture of two pure substances. In addition, vinegar is a homogeneous mixture. If you were to take a sample of vinegar at the top of that container, at the bottom of that container, it's going to look identical throughout. A heterogeneous mixture, on the other hand, is not identical throughout the sample. So if we look at this loaf of whole grain bread, we see that we have the seeds embedded throughout the bread. And if you were to sample one part of the bread versus another, you're going to get different ratios of the bread to those seeds. It's a heterogeneous mixture because it's not identical throughout. One characteristic of a mixture is that it can be separated. So you can separate out the different compounds, turning that mixture into pure substances. The way in which you separate mixtures depends on the different properties of the different substances. Depending on those different properties, you would use different techniques to separate the pure compounds from each other. You could use distillation if you had at least one liquid, where you're essentially boiling off the liquid and collecting that liquid. If you have different liquids, those different liquids are going to boil at different temperatures. And you can use that to separate out those liquids by slowly increasing the temperature such that you distill off different liquids. You could use chromatography. So chromatography takes advantage of the fact that different compounds will stick to other compounds at different strengths. So, for example, in this mixture, we have some different dyes. That yellow dye is adhering to that paper more strongly than that blue dye is. So as you run water up that piece of paper, you could, in theory, collect that blue dye, then collect the red dye from a mixture, then collect that yellow dye. If you had a solid and a liquid suspended together, you could use filtration, where you have a porous piece of material that you pour the liquid through. The solid gets stuck on top of that porous piece of material, and the rest filters through. Finally, we can use a chemical conversion followed by a physical process. So in this case of this penny, we can change the copper in that penny to a different form of copper and then perform a distillation or a chromatography or filtration to help separate out that copper from the rest of the material that's in there. All of these separation schemes rely on either a physical or a chemical property of the substance. And we're going to define those in a minute here. When we talk about different properties of substances, we can talk about them in terms of physical or chemical properties. A physical property is something that's observed without changing the identity of the substance. So these types of properties include things like melting points, the temperature at what a substance melts, boiling points, odors, masses, and the like. For example, in that example of the vinegar, we had water and we had acetic acid. We can take that water out from the vinegar by boiling. That water is going to boil at 100 degrees centigrade. The water will always boil at that temperature at sea level, but as we boil it, it's going to remain water, regardless of the form of matter that it happens to be in, solid, liquid, gas. Physical properties can be intensive or extensive properties. An extensive property depends on the amount that you have. So, for example, mass. You could have a kilogram of water, you could have 2 kilograms of water. That property is changing, but it's still water. An intensive property does not change. So, once again, we can go with water. So pure water will always melt at 100 degrees C. It doesn't matter if we have an ice cube or we have an iceberg. Getting back to mass, a mass will change depending on the amount of substance you have. So 3 kiwis is going to weigh less than 5 kiwi slices. A chemical property describes the way a substance changes or reacts when it is converted from one substance into another substance. In order to observe a chemical property, you have to subject that substance to a chemical change. For example, we can look at hydrogen being converted into water and heat upon its exposure to oxygen in an ignition source. This is a reaction that some people call the Hindenburg reaction. In order to observe the water and observe the heat, the hydrogen and the oxygen molecules have to undergo a chemical change. So that brings us to the end of this video, which was long because we had a lot of definitions to go through. In this video, I would say that the key takeaways is that chemistry is the branch of science that involves the study of matter and its interaction with matter and or energy. We divide energy into potential energy and kinetic energy. So potential energy being the energy an object has due to its position or internal stresses, and kinetic energy, the energy that an object has because of movement. Matter is simply anything that has mass and volume and therefore has density. Atoms make up elements. Elements are substances that cannot be broken down any further. We define a compound as a substance being made of two or more elements, and a molecule is the smallest unit of a compound. Because we're not concerned with plasmas in this course, we're only going to be concerned with three states of matter: solids, liquids, and gases. We can divide mixtures into homogeneous or heterogeneous. So homogeneous being mixtures containing two or more compounds that are uniform throughout, and heterogeneous mixtures being those that are not uniform throughout. We can separate mixtures based on either chemical or physical properties and do different techniques to separate those. And all substances will display both chemical and physical properties and can undergo both chemical and physical changes. So that brings us to the end. The next video will be a much shorter video dealing with SI units.